Welcome to our discussion on finding zeros of polynomial functions. All right, let's first take a look at Descartes' rule, which comes in two parts. There is Descartes' rule for the regular function. So let's say we just have, here's our function f of x. It says if we have a polynomial function with real coefficients, so the coefficients all have to be real normal numbers, so decimals, fractions, just can't be complex or imaginary numbers, and it's written in the proper descending order, which means the first term is the highest power, and then it goes down each power, right? Each smaller power. If there are missing powers, that's fine, but they just have to be in descending order down to the constant term. Then we know the number of positive zeros of this function is either equal to the number of times it changes sign or that number subtracted by an even integer. So in this example, we start with a positive, then it becomes negative, then it goes from negative to positive, and then it stays positive. So there are two sign changes. So we know that the total number of possible positive zeros, meaning positive numbers that end up being zeros of this function, like if we plug in 2, it becomes that function equals 0. If we plug in positive a half, it equals 0, that kind of thing. There's only either 2 or 0 because you'd subtract that number by an even integer. So subtract it by 2, gets you to 0. Subtract it by 4, which gets you to negative 4. Gets you to negative 2, which is impossible, right? So our only two choices are either 2 or nothing. We can also check to see how many negative zeros we have in our function by taking our function, evaluating it at negative x, and then redoing the same rule. So let's say this was our original function down here, x squared plus 2x plus 1. Nice, simple function. We know that function has two zeros because we know that function is actually x plus 1 squared. And if we set that equal to 0, we know that negative 1, right, x equals negative 1 works, right? This thing factors out as x plus 1 times x plus 1. Well, if we use Descartes' rule, we have to evaluate this function at a negative x. So you plug a negative x in here, but negative x squared is still just positive x squared. Negative x times 2 gives you the negative 2x, and then of course the 1 doesn't change. So now it goes from positive to negative to positive. It has two sign changes, which means according to Descartes' rule, we're either going to have two negative roots or none, right? 2 minus 2 is 0. And you go, yeah, but I only have one negative root. Ah, but you don't. You actually have two. You have negative 1 twice. It has multiplicity of 2, which means it's counted as two zeros. Yes, I know it's still the same number twice, so technically we really only have 1 0, but in the eyes of Descartes' rule, multiplicity means different zeros. So this is actually two zeros, and it fits the rule now. Here's another example. With this polynomial, we can check the signs. We go positive, negative, right? It stays negative, then it switches and switches, so it's either 3 or 1. When we look at the negatives, right, we evaluated at a negative x, we get two switches there, so it's either 2 or 0. So we know this original function either has 3 or 1 positive zeros, 2 or 0 negative zeros, and we know it has a maximum of 5 because its power is 5. And we talked about this in a previous lesson, that the maximum number of real zeros is always the power or the degree of that polynomial. So at most we're going to have 5, but we could have less. Okay, how about finding bounds for what those numbers possibly could, right? We now know how many we can have. We're going to either have 2 or 0, right, or 3 or 1, that kind of thing. But what could those numbers actually be? Well, if we have some polynomial function with real coefficients and a positive, that's what's important, it has to have a positive leading coefficient. That means the number in front of the highest power has to be positive. If it satisfies all those rules, and even if you have a polynomial that doesn't have a positive leading coefficient, you can just multiply it by negative 1 and turn it into one that is, and then the rules work. You might be thinking, well, if I do that, I've changed it. Yes, you have, but you can still find the zeros. And once you have the zeros of that new polynomial, they're going to be the same zeros of the other one, because you're just multiplying it by a -1. And so it's still going to have the same zeros. That's the beauty of it. Okay, so suppose this function is synthetically divided by x minus k. Now, if k is a positive number, and each number in the last row is either positive or 0, then we know that number is an upper bound. So that means all of the possible zeros have to be smaller than whatever that number is. If, however, you did synthetic division with a negative number, and then the last row has alternating signs, it goes positive, negative, remember that zeros can be regarded as either, then we know that's a lower bound. Any other combination tells you nothing. So let's look at an example. Find the upper and lower bounds on the zeros of this function. Well, we know the possible zeros are of the form p over q. And remember, p are just factors of the of the constant, and q is factors of the leading coefficient, which in this case is 1. So you take factors of 6, divide it by 1, and you get just factors of 6. So these are all the possible zeros. So you start with 1 and do your synthetic division. So 1 times 1 is 1. Add these together, 0, right? Add these together, -5. Add these together, -6. Add these together, -12. They're not all positive. They're not all positive in zeros. So this is not an upper bound. How about trying it with the next one, 2? 2 minus 1. Again, we know it's not going to be an upper bound, and it's also not a solution because this isn't 0, right? So you don't even have to do the whole thing. You can tell really quickly if it's an upper bound as soon as you get that first negative number. All right. 6 minus 5, right? 3 minus 1, and then 3 times 2 is 6, and look at that. We got an upper bound, but it actually ended up being a 0 as well. Okay, so there's my upper bound. To find the lower bound, we would redo the process with negatives and see which one gives us the alternating pattern. Okay, how about complex zeros? Well, just to remind ourselves what a complex number is, it's something of the form a plus bi, where a is a real number and I is your imaginary part. A and b are always considered real numbers. It's just when you slap that I on it, that becomes an imaginary piece, a real piece, and when you put it together, it's a complex number. I, remember, is the square root of -1. Something to realize is that all real numbers are complex numbers in disguise. So the number 3 is really a complex number because it's the complex number 3 plus 0i. So if we take the normal number system of real numbers that we're used to dealing with and we extend it out to allow the coefficients of our polynomials to be complex numbers, then we call that polynomial a complex number. And if there is some z that is a 0, then we just say that 0 is a z or a complex 0 of the polynomial. So all we're saying is all the same rules apply. If you can plug a number into a polynomial that makes the polynomial equal 0, then that's a 0 of that polynomial. If you're now letting your world include complex numbers, and the complex number is the thing you plug into the polynomial, then that just means it's a complex 0. Nothing new. One extra little bit of information. Now that we're dealing with complex numbers, we know that instead of saying the number of zeros is less than or equal to the power, it's exactly equal to the power. So when we're in the complex number system, every nth degree polynomial has exactly n roots. So in this example, This polynomial here is degree 7. This is going to have exactly 7 roots. Some of them might be real numbers, some of them might be complex numbers. Remember, the real numbers are considered complex in disguise, right? 3 plus 0i. So technically, you get exactly 7 complex roots. It's just some of them might be real numbers. Which is kind of what this is saying when it says every polynomial has at least one complex zero, again, because we know that the number of zeros is equal to the power, right, the degree of the polynomial. And so it has to have at least one as long as our power is at least one. Okay. We can also expand that and say that because we know we have exactly n number of zeros, then we have exactly n many factors. But just like before, because the zeros might be the same number over and over again, the factors might be the same thing over and over again. A very simple example here. Here's my polynomial. It's degree 2, so I know it has to have exactly 2 zeros and therefore 2 linear factors. When I factor this out, it becomes x plus 1 times x plus 1. There's my 2 linear factors. They're not necessarily distinct, right? In this case, they're actually the same. And I really only have one zero of x equals -1, but because it happens twice, it has multiplicity of 2, and it technically is considered 2 zeros. Here's another example where, given all this information, we can put it together and kind of figure out what a polynomial looks like based on some of its properties. If we're given a polynomial, its degree of 4, so we know it's going to have exactly 4 linear terms. We need a leading coefficient of 2, and we want the zeros to be -1, 3, I, and -I. We can now figure out what it looks like because we know every polynomial can be factored to look like this. Some number a, which is the leading coefficient, and then a bunch of linear terms of the form x minus some number. And those numbers are just our zeros. So we plug in the 4 zeros they gave us, -1, +3, +I, and -I. Clean it up a little bit, and there it is in factored form. If we want to know what the polynomial actually looks like, you have to actually do some math. Multiply some things together and combine some like terms, and then blammo at the end, there is your polynomial that satisfies all those rules that they gave us. Lastly, there's this idea of conjugate pairs theorem to help us finding zeros of polynomials, and it basically says if you have a complex number as a zero of your polynomial, then its conjugate must also be a zero. So if 3 plus 2i is a zero of your polynomial, meaning if you plug that in for x, the polynomial equals 0, then that means 3 minus 2i must also be a 0. Which tells us that any polynomial of odd degree with real coefficients must have at least one real 0. Because from our previous rules, we know that this polynomial here has to have exactly 5 zeros, 5 solutions, because it's degree 5. If it has any complex solutions at all, they have to be in pairs because they have to be in conjugate pairs, which means there has to be an even number of them. So we're either going to have 0, 2, or 4 complex zeros. Since we know we have to have 5 total, if we had 0, that means we would have 5 real zeros. If we had 2, we would have 3, and if we had 4, we would have 1, and there you can see that we have to have at least one real 0. Here's an example, again, where they give us a description of what the polynomial needs to be, and we have to like find all of its zeros and then find the polynomial. In this case, we're just finding all of its zeros. It's degree 9, so we know there's going to be 9 zeros. They tell us that 2 is a 0 with multiplicity of 3, which just means it has the factor x minus 2 cubed, right? I had 3 of these. It tells us 4 plus 5i is a multiplicity of 2, so it showed up twice, but we know that its conjugates also have to show up, so there's 2 more. And then it tells us 3 minus 7i is a 0, but its conjugate has to be there. So there's the 9th one, right? So there's 3, 4, 5, 6, 7, 8. There's all 9 of them. The factorization theorem for a polynomial with real coefficients. It's basically just building on all of this previous knowledge that every polynomial that has real coefficients can be uniquely factored over the real numbers as a product of linear factors and or irreducible quadratic factors. It basically goes back to the idea that if you have something of degree 3, you know that it must have at least one real factor because it's going to have 3 total, right? If it has any imaginaries, they have to be in pairs. So it either has 0 or 2 complex, right? Ones that have imaginary pieces. So in this case, it has to have either 3 or 1 reals. So if something of a power of 3, right, a polynomial of degree 3, has to have at least 1 real, then that means that polynomial can be written as x minus c, there's my real piece, times the quadratic that can't be reduced because those are the 2 complexes, or the quadratic can be reduced, right, to some other x minus c1 and c2. And so it's either going to be listed as a product of linear terms or one linear and an irreducible quadratic. That's for power of 3. Can you see how as we add powers, the rule is just going to expand? For a power of 4, we know we have 4 total. So we know we either have 0, 2, or 4 complex, which means we either have 4, 2, or 0 reals, right? And if we have complex zeros, when you take they have to be in conjugate pairs. And when you take the 2 complex itself and its conjugate and multiply them together, you always get a quadratic. So if we had 2 of them, this would give us 1 quadratic, this would give us 2 quadratics, right? This would give us 1 quadratic and then 2 linears. This would give us 2 quadratics and no linears. This would give us no quadratics and 4 linears. Now take it up to 5. Same thing is going to happen with 3, right? That you're going to have either 0, 2, or 4, because they have to come in evens, and then that means we're going to have at least 1 real, because it's an odd, and the pattern just repeats. Okay, find the complex zeros of a polynomial given that 2 minus I is a 0. Well, because 2 minus I is a 0, we know 2 plus I is also a 0. If we multiply those two things together, right here, doing all this, we get this lovely quadratic. So there's our quadratic that doesn't reduce to reals, it only reduces to these imaginaries. Now that we have this quadratic, we know it's a factor of this big thing, and if we take this, which is a degree of 4, divide it by a degree of 2, what degree is going to be the remainder? You know, the other piece, the quotient, it's going to be degree of 2 as well, right? It goes back to the rule that if we have x to the 6th over x squared, it's x to the 4th, right? Top number minus bottom number. So if we have something of degree 4 divided by something of degree 2, the result is going to be something of degree 2. So if we actually did the division using long division, because you can't use synthetic here because you're dividing by a polynomial, you can only use synthetic for a linear term, right? Linear terms of the form x minus some number. When you do the work, there's your quotient piece. So that means my original polynomial is a product of these two quadratics. We know this one doesn't reduce, at least not in the reals. It came from our complexes, but we can try and reduce this one to linear terms, and it in fact does. And then here are our 4 linear terms. 2 of them are reals, 2 of them are imaginaries, and it still satisfies that rule that says the original polynomial is a product of linear terms and irreducible quadratics if we're talking about keeping everything in the real numbers. If we're talking about keeping everything in the imaginary or complex numbers, then it's always just going to be the number of linear terms is its power. It was a power of 4, so it has 4 total terms. Okay, let's put it all together, because what's the point of all this? The point of all this is to find zeros. We want to be able to factor polynomials, because we want to know, when does our polynomial equal 0? When does it cross the x-axis? Things like this function. It crosses here and it touches here, so it has 2 zeros. It'd be kind of good if we knew what those numbers were. Well, that's what this helps us do. So the first thing we do is we find the maximum number of real zeros by using the degree. So the degree of 5 tells us there's 5 total. Then find all possible number of positive and negative zeros using Descartes' rule. If you don't remember Descartes' rule, we'll remind ourselves here. We look at how many times the signs change, 4. Then we plug in the negative x and see that it only changes once. So there's a total possible of 4, or divide by evens, so 4 minus 2 and then minus again, right? So there's either 4, 2, or 0 positive numbers, and there's either 1, and there has to be 1 negative, right? Because you can't subtract 2 from it. So then what you would do is you would use synthetic division and start with 1, do the work, and then go from there. What I've done here is I've kind of gotten halfway done. Did synthetic division once, got a smaller one of degree 4. Then did it again, got an even smaller one. And each time you get a smaller one, you go back and you redo your steps. You notice, like at this point, this is x cubed squared, right? X, and then my constant term, this is now a power of 3. So now I know there's only 3 total zeros left. I can redo Descartes' rule and see that it changes sign twice. So it's either 2 or 0. And then there's still 1 negative. And then from there, we write out the set of all positive rationals, which I already did. 1 positive, plus and minus 1, 2, and 4. Because remember, that comes from P over Q. And then you just try them. You try 1, you try 2, you try 4. Whatever doesn't work, you get rid of them. Then you can test for upper and lower bounds using these rules, and then eliminate your choices. Because basically when you have plus and minus 1, 2, and 4, that means you have 6 possible zeros to check. You don't want to have to check all of them. So by using all of these rules, it just helps you eliminate possibilities. So instead of having to check all 6, you only have to check so many, because you know you're going to find an upper bound, you know you're going to find a lower bound, that's going to eliminate some others. You just want to be systematic about it. Okay, so that's the whole purpose of this, is to be able to factor these things out.